really happy to be here. Since the start of the pandemic, this is the first time I'm in a conference, and it's a really special conference, right? So we see a lot of innovation, lots of interesting projects, and I'm really happy to be part of this event. So I'm a performance engineer at Nubank, but actually, as John said, Nubank is actually a closure shop. I actually work for Cognitect, the creators of Clojure. So I don't do Scala anymore for a few years now, actually. And I used to be very active on open source in Scala, so I worked on Quill, monadless, and many other projects. But for the past 5-6 years, I haven't published anything. And this year, I decided to start working on something new. And the idea is really work on a performance challenge that I've been battling for many years. It's something that I see in many systems, in systems that use futures, or even functional effect systems like ZIO or CATs. And it's something that really limits the capacity of these effect systems to leverage the hardware in an efficient way. The JVM is really amazing. Like, it has just-time compilation, it optimizes your code, it generates native code at runtime through just-time compilation. But we have some issues with how we encode effects in Scala that make those optimizations not work well. So this is my goals. This is something I've been chasing for many years. So if you see the first line there is the itable stub. So I just took like screenshots from previous talks. So these are talks like from 5 years ago and etc. And it's always the same problem, right? So at the top, if you profile your ZIO application or CATS effects or anything that is using really monadic APIs, you're probably going to see the itable stub as the top item in a profiling session, right? And it's interesting because it's not only something that affects Scala. Like I said, I'm working with Clojure now, so I have another example there. And the itable stub issue is also there in Clojure, but it's much more mild than Scala. But it's something that's always like, I'm always chasing this problem and trying to solve it. I worked on just-time compilation optimizations for it. I worked on changing implementations in the Twitter future, for example, to avoid itable stubs. But it's still there. And I wanted, OK, maybe this year I want to do an open source project in Scala. Let's try to fix that problem. So what happens there is you have an interface dispatch. So for example, you have a call in your code, you have a method, and that method is going to call a function interface, for example, right? The JVM has profiling mechanisms that it starts interpreting your code and then seeing, OK, at this call site, I have these concrete types that are observed, right? So the JVM knows and estimates the types that are going to be on each of the call sites. And for example, here, the JVM might see that there are 2 implementations, function 1 and function 2. And this is actually a dispatch based on an interface method. So it becomes an interface dispatch that is implemented by the itable stub on the JVM. And when we see itable stub dispatching, it means that the inlining of the method failed. So the JVM optimizes our code by the most powerful optimization is really inlining a method that's being called into the caller, right? So if you have an itable dispatch, it means that that method could not be inlined by the JVM. So it failed to inline. And it means that that call also has multiple targets, right? So I'm not going to go into the details of the itable dispatch and how it works, but it's basically a lot of pointer chasing. Because you have multiple inheritance of interfaces on the JVM has to do a linear search on a table of interfaces, and then from that linear search go to a table of offsets for methods, and then from that you have to go to a method in the meta space, and then from the method in the meta space you have to go to the native pointer of the implementation of that method. So it's a lot of pointer chasing, right? So, and if you have multiple interfaces, it's even worse. And this is something that's really a big problem for functional programming nowadays. So I wanted to explore how this happens and why we have this problem. If you see the effect systems that we have today in Scala, or even in the JVM in general, they normally work with a kernel, right? So you have basically something that is like a while loop that is consuming transformations and executing them, right? So, for example, you can have a computation that is a map, and then a flat map, and then another flat map. And the kernel is basically that thing that's consuming those computations. And, for example, it picks up the map for execution, invokes its function, makes a transformation, and then it can pick up the flat map for execution. And flat map is a bit more complicated because it can produce another computation, right? And in that case, basically, the flat map can, for example, produce 2 new maps that are going to be executed before that initial flat map that would be the next one. And the kernels of the effect systems basically work in these modes of always with this while loop and executing functions, executing transformations, right? So within that kernel, there is one call, or maybe a few calls, that invoke those transformations functions, right? So you have there, for example, function call that's going to be called for maps or flat maps. But for our examples, we are going to consider that the kernel has only one call. But it could be just a few, right, depending on the type of the transformation. But if you think of this problem, right, as we saw before, if you have multiple implementations, you end up with dynamic dispatching, right? So if you have a call in your kernel code, for example, ZIO's runtime, cat's effects runtime, there's going to be that call there, and it's going to invoke, I don't know, hundreds, thousands of function transformations, right? So think of all the transformations that you have in your codes, all the maps, flat maps. These are all classes. These are all function classes that need to be invoked by the kernel. And that call is going to be polymorphic. The invocation of those transformation functions are not going to be in line with the kernel because it's basically hundreds or thousands of implementations. It's not possible to inline them. And just to show a more concrete example, let's say that we have 2 transformations, map and 2 maps, right? And this is a scenario that's very common for benchmarks, and it's not really what happens in real applications. That is, we have only 2 functions. Let's say that the whole application is only these 2 transformations. In that case, we have only 2 functions that call within the kernel has to perform, right? So it's going to call +1 and then the other +1. And in the JVM, the default just-time compiler C2 has inlining for bimorphic calls. So if you have 2 implementations of an interface in a call site, the JVM is going to be able to inline the body of those 2 methods. Not in all cases, but generally. And in this case, it will be possible to inline. And in the end, like the kernel is going to actually have those 2 functions at runtime inlined and compiled within the kernel itself, right? So you end up with something that's very lightweight. The JVM is able to basically avoid allocations of integers, boxing, and even, I haven't tested with ZIO or et cetera, but in theory, the JVM could even squash the +1 and +1 to +2. The JVM is really powerful. It does a lot of very interesting optimizations and deep optimizations. But that's not really what happens, right? We have, for example, if we have 3 functions now, and the kernel call is going to call these 3 functions, it's not bimorphic anymore. There are other just-time compilers that are able to inline more than 2 implementations, but in general, this is going to fail to inline. So what happens is when you are going to call, when the kernel is executing this computation, it actually has to do the interface dispatch. The implementation of the transformations cannot be inlined with the kernel. And that means that each transformation is its own roles for the just-time compilation, for the optimizations of the JVM. So it's not going to, for example, if you have 2 transformations that do like +1 and +1, it's not going to be able to see, okay, I can avoid boxing to invoke the function. it's going to have to box and create an integer to invoke those functions. The functions are not going to be squashed together, so it's not going to be optimized for execution. So if you start to think more about this, imagine like all the transformations. I don't know, maybe you have, 2,000 transformations in your code base, or 3,000 or 10,000 transformations in your code base. It's not possible to inline those with the kernel. And that means that each transformation becomes its own unit of work, its own unit of optimization by the JVM. And this is a fundamental issue with effect systems on the JVM today. So this is what I call interpretation overhead of effect systems in Scala on the JVM. So just to summarize, you end up with dynamic interface dispatches. This is something that's expensive. The dispatch itself is expensive, and you can simplify in sessions, but there is a bigger problem. It's actually a symptom that the implementations, the transformations, are not having inlining between them. Each transformation becomes its own unit of work for the JVM. And the second thing that I wanted to tackle, besides the performance aspect, is the usability aspect. When we see effect systems in Scala, it's really amazing the kind of things that they can do, but at the same time, you can see that there is something missing, like things are not really composing from an effect aspect. And ZIO is a really amazing advancement of that, but it's still, I feel there is like too much, it's the lack of composability of effects, how hard it is to work with multiple effects is really a usability problem today for functional programming. And I would say that monad is actually probably the best, worst thing that could ever happen to functional programming. It's an amazing, amazing abstraction. So you can take a runtime like the JVM that has no async or asynchronous effect, and then you can implement something at the user level that has asynchronicity, right? Or you can have, like, I don't know, some environments like in ZIO, like you can have like build things that are really, really amazing on top of monads. It gives you a level of abstraction that is basically almost like a user level language, right? So if you see ZIO, for example, you can do ZIO in Scala, and now you can do ZIO in TypeScript. I was talking to Andreas from Diverge yesterday, the day before yesterday, and we were talking, he's using ZIO in TypeScript, right? And it's actually, it feels like the same thing. Like you're just using the same language, the ZIO language, on top of another syntax, another language. And that's really, really interesting about monads. But at the same time, like, you have really high syntax overhead. That's something that bothers me for a long time. I see many people, especially people that are newcomers to the language, like struggling to write things that would be like half an hour for them in an imperative mode, right? And they take, I don't know, 1 day, 2 days to write using monadic interfaces. So that's really something that I wanted to try to tackle as well. And monadless and ZIO Direct that is inspired by monadless was my initial work on that. And what I'm going to present today doesn't have a better solution still for the syntax overhead, but maybe we are going to be able to integrate with ZIO Direct at some point. And the second thing is that monads don't compose, right? So if you have an effect in a monad, that's like its own world. It's really hard to make it play with other effects that you might have. So for a long time, I was very bored with the Scala community, to be honest. We have like this paradigm that was created many years ago, that is, we have like this kernel that is this monadic engine, and then we have all these awesome effects that we want to use, right? So we want to be able to do timeouts, we want to be able to run things in parallel, we want to be able to use options, lists, perform I/O, batch queries to remote services. We want to do these awesome things, right? And then someone came and said, oh, we are using monads, and this is going to have an I/O API boundary, right? And then we had to choose. Some things can be encoded as within the I/O monads, and some things cannot. So we had some effects that were left behind in that process, right? And then there were solutions for that side of outside of the I/O interface, but they are, in terms of performance, that is what I'm interested in. They are not really viable in terms of monadless transformers, monad transformers and these kind of solutions. And for a long time, it was like, OK, we have all these awesome effects. I'm going to implement a new effect within the I/O or some monadic interface and try to bring back some of those effects within the effect system. But there was always the monadic Karen around, right? So there was like always those monadic people saying, you are breaking the laws, you are killing babies, like unicorns are dying because you're breaking the monadic laws. And it's boring. It's just boring because this is not innovation, right? Innovation is about breaking rules and creating new rules. It's about really changing how we think about problems. And only thinking about problems in terms of existing patterns limits what you can do, right? You can, for example, break laws for a while and then find new laws. Or you can break the laws with a new solution and eventually see that you have a way of not breaking some existing laws, right? Patterns are great only when they guide you, not when they constrain too much what you can do in terms of innovation. And when I saw ZIO years ago, to me it was like really a refreshing moment. I was like, OK, this is so boring. Like, we can't do all those effects. Like, it's something that's not really working. And ZIO came and like, OK, now we have a better way of doing effects in Scala. And it's really amazing if you think. ZIO has like the same boundary of the ZIO API, of the monadic interface, but it's able to expose two channels for effects. That is like the error channel or the abort channel and the environment channel. And that brings like a lot of power to ZIO, that, as we see today, right? So for example, ZIO took the either effect that actually the error channel in ZIO, I would say it's basically the either effect that you basically have a computation that either is going to produce the value you are expecting or it's going to halt with a constant value, right? And when ZIO put the either like between the interface, right? So it's as a type parameter, then it opens the possibility of having effects that are going to abort, halt the execution, right? So it's a lot of effects can have this kind of behavior. And for example, option could be within the ZIO effect system now, right? So that's something really, really exciting. And then ZIO, like for example, with zQuery, the bindings on top of the API, and very close to the ZIO API with really good performance and not too much overheads, without like all the issues with monad transformers, for example. It's a really interesting innovation in this space as well. And the environment effect is just simply too amazing. Like it opens like so many possibilities of what you can do because you can basically inject some implementation that's going to have other effects. And that's something that you can model, can use to model many types of things that you can do today. But we are engineers, so we always question things, right? So I started questioning, maybe there is another way that we can tackle this problem. So this was my crazy idea, I don't know, beginning of the year, and I've been pursuing that, and I'm going to present a solution for it today. That is, instead of having the boundary with effects within it, let's try to move that boundary and have only the kernel within the core of the application. So that means that we have to be able, with that boundary, with that API, express all those effects, right? So you have to have a way of composing those effects and expressing them within that kernel. And the second idea is, in Scala 3, we have the inlining, compile time inlining of methods, right? So with the compile time inlining of methods, we could generate multiple call sites for the transformations and avoid the polymorphic inlining, the itable stub issue. So, but that's not so easy, because if you have a kernel that's too large, you can't really inline the kernel within each of the transformations, right? So the idea is, what if we can have a kernel that is extremely small? Right, so that was like the two principles, the two things that I basically tried to look for, right? So trying to find a solution with those two characteristics. So the kernel could be in line with the execution and not be something that's opaque to the JVM for optimization. So that's the project Kyo. I'm actually making it public today. It's a new encoding of effects in Scala. And it's an interesting approach. It's still experimental. This is like the first time I'm actually sharing in public. I shared only with a few people. But I'm really looking forward to the feedback because I feel it's something that can be, maybe it's the first of a new kind of effect system with a microkernel, something that can be more performance on the JVM. So I wanted to clear two things before I start talking about Kyo itself. The first one, I've done a lot of macro work over the years in Scala, so many people are going to think this is some macro magic. It's not macro magic. I do use the inline from Scala 3, but as a performance optimization. There is no macro trees or transformation of your code. It's all pure values and pure functions. I have, even I put in the builds, there is a step to remove all the inlinings, run the test, and the test still pass. So no macro magic. It's inlining only for performance. So everything is basically a pure value or a pure function. The second question is it a monad? And my answer is, I don't care. Really, it's about innovation, and breaking rules is part of innovation. I do have a test with the ZIO I got from Adam that tells that it seems to be a monad, but I don't know, like, does it matter? It's much more about, okay, what are the properties of this solution? How can we reason about it? Are there new laws about it? Or how they play with the existing laws? So now I'm going to start presenting the solution. I wanted to first show you how the types of Kyo computations are expressed. Kyo is basically an answer for this problem. What color is your function, right? But it's actually, it's not a function, it's value, right? So what color is your value? And ZIO is also that, right? So what color is a ZIO computation? The color is, okay, it can abort with these exceptions. It requires these environments. And Kyo is the same principle, right? So you have a value that expresses what are the effects that it has, right? And the way that Kyo does that is with this infix type that is greater, and it has two components. So the first one is the type of the value of the computation, so it would be basically the third parameter of the ZIO computation, and then there is a set of effects on the other side. And these are effects that are suspended, something that you want to perform, but it's suspended, and eventually they are going to be handled. So you basically suspend an effect, and then eventually you handle. That is the paradigm from algebraic effects, right? And the effects type parameter is actually just a type level set. It doesn't represent a type of a value or anything like that. It's really a way of encoding using some types in Scala 3 type level set of effects that are suspended for a computation. So one example is you can have an integer that has the options effect suspended. Or you can have an integer that has no effects. So if you have nothing, it means that no effects are pending for handling of that computation. Or you can have an integer that has two effects, options and tries. You're probably noticing that there's like this pattern of plural, right? The way that I decided to encode effects in Kyo is you have the regular monads or something that you want to lift into the effect systems of Kyo. Basically, the effects are the plural of what they are handling, right? So if you have options, it's an effect for option. If you have tries, it's an effect for try. If you have futures, it's an effect for future, right? So it's this kind of pattern for the name of effects. And then you can also have something like ZIO. This would be the equivalent in Kyo of a ZIO computation. So you can have an integer that has the abort effect with timeout exception and requires an environment, a value of service 1, right? Cool, so that's how the computation, the types are defined. But let's see how we can create those values. For example, let's say that we have an option of integer, option of 1, and I want to suspend using the options effect. I just use a similar syntax from the type level, but this is an actual operator, the greater operator. And that's going to basically lift the computation into options. So we are going to get an integer that has the options effect suspended. Make sense? And then we can also have multiple effects, right? So we saw that the effects type parameter is actually a type level set. So let's say that we have an option of try of integer. So if I suspend options and then I suspend tries, that's going to basically suspend the two effects, right? So if we look at the types of those computations, for V1, we are first lifting, suspending options, right? So we end up with a try of integer with the options effect suspended. For the second computation, I'm lifting now the tries effect. So that's going to be an integer with the options and tries effects suspended. Make sense? So that's like how you basically suspend effects. So that's one side of the thing. And this is where basically you are at an abstract level, right? So you are not really handling those effects. You don't know anything about those effects. In fact, Kyo can have an effect that cannot be handled. You have to provide a handler later to basically handle that effect. So how can we handle those effects? So going back to the same example, an option of integer and suspending the option effects. And then I can handle, the handle is basically the opposite, so it's the lesser sign. And you basically you move the option to the effect because you're suspending it, and then you bring that option back and you get an option of integer with no effect suspended. And there's something interesting about Kyo. If you have a pure value, something that has no effects pending, that's actually just a value. Because Scala has opaque types, in Kyo, the type is actually an opaque type, and the implementation of the opaque type is a sum type. At runtime, there is no wrapper. If you have a pure value that has no suspended effect, it's just that value. There is no wrapping. There is no boxing into something that's going to represent, because opaque types give you like a lot of power to do this kind of work. So if you see, the V2 is an option of integer with no effects pending, suspended, so it can actually just be converted to option of integer. So there is a conversion between t of nothing to t and and t to t of nothing, right? So there's like this conversion. Cool, so let's see another example. We can also have multiple effects being handled. So let's see the example where we have an option, a try, and then we lift option, lift try, and we end up with an integer that has two effects suspended, options and tries. In that case, I can handle things in different ways, right? So I can handle, for example, options first, and then tries later, right? So in that case, I'm going to get a try of option. That is basically following the order of handling of effects. The way that the execution is going to happen is actually dependent on how you handle the effects, not how they are used or suspended. How you handle effects is what really matters. Or you can do the opposite. You can handle tries and then handle options, right? So you end up with an option of try of integer, right? So handling the effects is what really produces the execution of suspended effects and determines how those effects are going to be executed. Another example that shows how the execution changes when depending on how you handle effects. So let's say that I have an option of try, but now it's going to throw. It's going to be a failure, right? And then I lift option, lift tries, but I do I execute it in two different ways. So the first one is options and tries, and the second one is tries and options. When I execute this, the first one is going to return a failure with the exception, and the second one is going to return a sum of failure, right? Because as we saw before, these are like the type interfaces as well. For the first case, when you're handling options first, it's going to try to execute the computation, and it's going to fail with the transformation with the exception, right? And then the tries effect is going to catch that. But if you handle try first, the tries is going to handle that exception, and then when it gets to option, then it's going to be a pure computation, then gets lifted to sum of failure, right? And then some of you might be thinking, okay, can you really do that to all effects? And yeah, these are shallow handlers. There are also deep handlers. Some effects can't be encoded in a way that's convenient for like handling and suspending effects. And there is a separate way of doing that that are deep handlers. I'm going to talk about that later. Cool, so now we know how to express the type of the computation. We know how to suspend an effect and handle an effect, but does that matter, right? We have to be able to implement transformations, like do maps and flat maps. So how do we do that with Kyo? You can just do like you do that with monads in general. So you can just do a map plus one, for example, right? Or you can do a flat map. In this case, I'm flat mapping an integer with options to an integer with tries. So I'm going to have an integer with options and tries, right? I'm flat mapping with the two effects. And if you remember, actually, Kyo has this property. If you have no suspended effects, you actually have the value itself. So the difference between map and flat map is not really a necessity for Kyo, right? Because the difference between map and flat map is that you have the wrapper type or not. So Kyo has the apply method that is both a map and a flat map. So you can, instead of deciding, oh, should I use a flat map or a map, you just call apply with the same transformation, and it's going to have the same behavior. Or you can apply with a transformation that's going to have a new effect suspended, right? So that's something that you can do without worrying about maps or flat maps. And it's very similar, right? It's just like, if you don't need to put like dot map or dot flat map, just call the apply method itself. You can also use for comprehensions with Kyo because it has the map and flat map methods. So you can, for example, suspend the option. The second line is very interesting because if you had regular monads, you would have to do v2 equal and then the computation, right? Because Kyo has this property of pure values also being member of its type, right? It's a T of nothing. Then you can also do maps and flat maps on pure values as well. So you can do something like the second line, not have like a different syntax for a pure value, pure transformation. And this is basically the same computation as we saw before. Cool. So this is like the handling and like the easy part. The hard part is deep handlers are more complicated. But at the same time, many effects like bars or options, tries, they all can be encoded as shallow handlers. But some effects cannot be encoded as shallow handlers. If an effect cannot produce, so if you have an effect of T, right? So a list of T, for example, or an option of T. To be a shallow handler, it needs to eventually converge to T or a halting value. So if you think of option, it's going to converge eventually to none or to the value if it's sum, right? So you can resume with the value. With deep handlers, that's not, there are some effects that are not like that. So if you have a list of T, you can't really converge eventually to T because you have multiple instances of that value. And that's where deep handlers enter. And they are more rare, and they are a bit more involved, but they encode effects that are more powerful as well. So an example of effect that is a deep handler is the lists effect. So you can, for example, suspend a list using the lists effect, and then you can apply a transformation, for example, +1 on that suspended effect, and then you can handle that. But now the handling has two lesser, it's a different operator, right? Two lesser operators, because that's a deep handler. And if you have only one deep effect, that's very trivial. It's very similar to shallow handlers as well. And this is going to produce a list of 2 and 3, right? But if you have more effects, then it becomes a bit more complicated because you have to, the runtime Kyo needs to know how you want to compose things in more detail. So, for example, here I have a list an integer with the lists effect suspended, and then I flat map or transform to a computation that's going to fork the execution using a future. Right? So now we have an integer with 2 effects, lists and futures, and the way you have to handle that, you have to provide, okay, I'm handling first futures, but I want to, if I have lists, Kyo needs to know how it's going to reorder the effects so it can produce a future of lists, right? So if you think of the computation, what's happening there, the V1 is suspending a list, and then eventually for each element of the list, I'm forking with a future. So within the runtime, I have actually a list of future, right? So how can Kyo produce a future of list without knowing more about the effects? And that's where this syntax of providing how the effects compose together, that is similar to monad transformers and etc. But with a much better execution, there isn't like the pattern of nesting of execution and lots of allocations. It's really applies only where it's really necessary in terms of composition. But for example, here I can say that if I have the lists, a list of futures, I want to sequence them to a future of lists using the sequence method from futures. And that's going to produce a future with the success, with the list, with the value +1, right? Cool, so some effect examples. This is the options effect. So this is the entirety of the encoding of the option effect. The options value is actually something that I have to encode as a singleton, but if I use an object in Scala, it's going to be like the object type, so it's a bit more complicated. It's not nice for the API, so I normally create a new class that's final and only local, and then creates one instance of that effect class. And then I provide a shallow handler. So the shallow handler has the pure method. So if you are handling an effect that actually, a computation that actually doesn't have that effect suspended, right? So you can do that with Kyo as well. In that case, it needs a pure method. So it's going to basically lift a pure value into the container of that handler. And the second one is the apply method, and that's the interesting one. So that's where it's going to handle the effect itself. So the first parameter is the option itself, and the second parameter is the continuation from the point of suspension of that effect up to the point where the effect is being handled. Right, so, and this is a pure method. It's a pure function. It's not, if you see other encodings of algebraic effects in Scala, you're going to see some magical resume function that is like doing something special with different type signatures. In Kyo, it's just a pure regular function. It's not something different. And if the option is none, what Kyo does is just short-circuit the computation. So abort the computation saying, I'm going to continue returning a none, and suspending again the options effect. But if it's a sum, then I can resume with the value of that sum. The other example is the lists effect. That is a deep handler, it requires a deep handler. The first parts of the effect itself is very simple. And the deep handler has the pure method as well. There's an override of map just for performance reasons. It's not really necessary. And the interesting one is the flat map one. That is basically a monadic interface, right? So deep handlers are basically monad interfaces. So there's something I worked, so all that you saw until now is something that I've been working on for a while, but the ZIO integration is something new, so it's very, I would say just a prototype, but I think it's an interesting way of showing how powerful Kyo can be. So this is a random example of a ZIO computation that uses service 1, can throw illegal state, and produces an integer, maybe produces an integer. And you can lift that into Kyo, and it's going to basically transform those error channel and environment channels to Kyo's effects, right? So you're going to have an integer that has the environment's effect with what you require in terms of environment, with the abort's effect that is might abort with illegal states, and with the ZIO's effect, right? So and ZIO is going to be a deep handler as well because ZIO needs to have control of the execution. And then you can, for example, provide the environment variable that you are requiring. So you can just say environment let service1 and then v2 and +1, something random, right? And that's going to basically get rid of the environment effect that was suspended. You can also handle the abort effect and then transform the abort into either. Abort is very similar to either, but it's allocation-less if there is no exceptions. But it's very similar to either, and there is a method to convert it to either as well. And then lastly, you can handle the ZIO's effect as a deep handler, and that's going to give you back an actual ZIO value, for example, a ZIO task here. I just wanted to talk about the environments effect. That's also in core. It's not in the the ZIO integration. It's an interesting effect because you can basically summon something like in ZIO. You can summon a service. So you can say, OK, I have to have here a service1, right? So I just call the apply method, passing the type I need, and that's going to give me a suspended computation that has that value, but with the value suspended as an environment as well. And then you can, for example, provide a service that actually has a dependency on other service, right? So ZIO also has something like this for the environment. And in Kyo, it's really within the computation and the regular effect itself. So you can, for example, say I need service2 to provide the service1. So I just use environments, and that's going to give me a service1 that has the service2 effect pending for handling. And then I can let that service1 and then use it, and etc. But that's going to still require service2, right? I'm using service1, and it requires service2. But I can just continue executing the computation as if I had the service1. The service2 is going to be suspended as a pending effect to be handled. And then I can create service2, and then I can provide service2, and then finally I get the integer that I was expecting. So just to finalize, because of the performance constraint, and the idea of inlining the implementation with execution, I tried to find something that's very, very minimal, very simple. And all that you saw until now, it's really powerful, right? You can model the error channel, you can model the environment channel, you can model options, futures, many kinds of effects. But the code is very small, right? So this is all classes in Kyo's core, and you can see the effects that are implemented so far. But the core itself is about 200 lines. Right? If you compare it to the size of the cores, the kernels that we have today for effect systems, it's really a different kind of paradigm. The implementation of the effects are also very small. There is aborts. There's also something that's very interesting. I don't know if ZIO has something like that. That is, you can stage a part of the computation using an arrow, and then you can avoid a lot of allocations and get better performance. There is something like zQuery for batching, and then environments, futures, I/O as well, and multiple other effects. So that's the presentation. The project wasn't public until today, so feel free to check it out. I'm sorry I didn't have time to create documentation and the README, but I'm going to push something soon there. And yeah, I think that's it. Thank you.